All right. Good evening, folks. This is our second to last lecture where we're going to be going through content. Just as a reminder, next Monday we will not be meeting at night. It is Memorial Day. We do not have classes. And the following Monday, that is June 6th, June 7th. Monday, June 7th. That is going to be our last night of lecture. On June 11th, that Friday, you guys will have your final versions of your space mission assignments due. That includes the supporting documentation. And then on the following Monday, we're going to do those presentations. That is the plan. I will be getting the feedback to you this week if you submit it on time. And you should then have a solid 2 weeks between when I get it back to you and when you actually give your presentation, okay? Are there any questions or concerns from anybody there? Ian?
Yeah, so just to be clear, you said that the 14th is when we're all going to be presenting here at the same time.
Yeah.
Hello, how are you?
All right. The reason why I'm bringing that up is because I'm going upstate for 2 months starting on the 15th, and I remember that that's a night that my family originally had planned to get everything and check for myself, but I'll make sure that I'm here for this.
Great. Okay, very good. All right, folks. Well, then let's get started. How many of you had a chance to watch the lecture from earlier? I feel like yays would be far and few between for that question. Okay. So earlier we finished up talking about the stellar evolutionary tracks of high and low mass main sequence stars, and just sort of touched on this idea of like the cosmic recycling, right? That you have all of this gas, these clouds in space, this dark dust called the interstellar medium, and stars form, stars evolve, stars die in a supernova, and then that material from the supernova just becomes interstellar medium, which starts the cycle over again. So it's very much, like an ashes to ashes kind of situation. Okay, we're gonna move on to something else. I foresee tonight's class being very short. I promise to anybody that that is watching this from the earlier section that one of these days I'll make our Monday class short, because the evening class seems to always get the better end of the deal here if we finish everything early. All right, so we're going to talk about gravity for a little bit. So let me just get my slides pulled up here. Share my screen. You know what? Hold on, let me just do this one more time. Might as well share my sound and everything while I'm doing this. Okay. So earlier in this course, we talked about gravity according to Isaac Newton, and you all had a lab on it, where we look at this equation boxed in the yellow. That is Newton's law of universal gravitation, and it describes the force with which two masses will pull on each other when they are separated by some distance r. And so let's say that right now, this very second, the sun just disappeared. How long would it take for the Earth to know that the sun is gone? You know, how long would it take before the Earth stopped orbiting a sun that's not actually there? What do you think? All right, please chime in. What does your gut tell you? What makes sense to you? Share with the class. If the sun disappeared right now, how long would it take for us to know? So Mario in the chat says instantly. Instantly. Does anybody, how many of you agree with Mario? If the sun went out right now, we would see it go out right now. Jaring agrees. James agrees. Okay. And according to Newton's law of gravity, that would be correct. Right? According to this law, the change would be immediate because in this equation, time is not a factor. But then comes along this other guy, Albert Einstein, and he did not agree with this idea that that it would be an immediate, an immediate thing, right? He didn't believe that you would instantaneously know that the sun disappeared. Because through his work, Einstein showed that the speed of light is the fastest thing in the universe, right? The speed of light, or the speed with which light travels in a vacuum, is essentially the cosmic speed limit. Nothing can travel faster than light travels through space. And if you ever do any research on anything that Einstein has said, specifically if you do any research on special relativity, you'll see he said a lot of interesting things. Right? We tend to believe that if I have my stopwatch and you have your stopwatch, and I get on my spaceship, and and we both we synchronize our watches, we start at the same time, and then I get on my spaceship and I travel around the planet and I come back, you would probably think that our watches or our clocks would be exactly the same when I get off my jet, my rocket. But the reality is they would be different, right? Because the person in the rocket is moving faster than the person on Earth, and that causes them to experience time more slowly, right? And so we talk about like time dilation, right? Time is not fixed. Neither are length measurements. For a person traveling really fast, objects appear smaller than when you're not moving relative to them, right? And all of this is based on the idea that the speed of light is constant. So no matter how fast you're moving, the speed of light is going to be the same for everyone, no matter what their frame of reference. All right, and so Einstein's saying, well, that makes no sense. How could information like gravity travel faster than the speed of light? If it takes sunlight 8 minutes and 20 seconds to get from the sun to the Earth, then that makes no sense. We wouldn't see it disappear immediately. If the sun disappeared, we would see it disappear in 8 minutes and 20 seconds from that, because there's still light coming to us from the sun. Right? There was light that was already emitted that's on its way to us. Right? And he said, well, that wouldn't make sense that gravity would just shut off, right? And that we'd be orbiting some like phantom star that's not really there, but we can still see it. That doesn't make any sense. And So in any case, Einstein comes forward and says, well, gravity has to travel at the speed of light, right? It doesn't make any sense that gravity's information gets conveyed immediately. And so we're gonna watch a short video right now. I don't know how many of you are familiar with Vsauce, the YouTube channel. They do a lot of good science videos, but I'm going to pull that up right now. Hold on. Okay.
Hey, it's Michael here.
Hold on. Okay, here we go. Can all see the big green screen? All right, here we go.
Hey, Vsauce, Michael here. Gravity is a property of matter, anything with mass. This includes the moon, Earth, Jupiter, the sun, and even you, your body. In fact, if you kind of like somebody, have them stand 3/4 of a millimeter away from you. At that distance, cumulatively, every atom in your body and every atom in their body will draw you two together with the same gravitational force that the sun is exerting on you right now. Of course, we don't feel either of those forces because compared to the gravitational influence of the Earth, they are basically nothing. You don't need to concern yourself with the gravitational attraction between you and someone you're hugging, or your individual body and the sun 150 million kilometers away. In fact, the sun may as well not exist. What if the sun disappeared? Well, to be sure, it's not going to happen. The sun will die billions of years from now by expanding, boiling off our oceans, and swallowing the Earth whole. The sun is not going to simply disappear. Matter and energy don't vanish. Of course, matter can quantum tunnel to different locations, but on the scale of the sun, there is not enough time in the lifetime of millions and billions of universes for such a probability to even be worth discussing. But let's discuss it anyway, as a thought experiment, to determine how the Earth would get along with no sun. What will the Earth do and what can it do alone? At the exact moment that the sun disappeared, we would have no idea, because it takes light from the sun 8 minutes and 20 seconds to reach Earth. So for a little over 8 minutes after the sun disappeared, we would have no idea. Once we did, confusion and mass panic would most likely ensue. The sun's gravitational grasp on our planet would also take 8 minutes and 20 seconds to end. This is because gravity waves propagate at the speed of light. So, the very moment we saw our sun disappear, we would also lose its gravitational influence, and Earth would fly out in a straight line tangent to wherever it was in its orbit. The finite speed of light and gravity mean that as panic and fear spread across the Earth at the loss of our sun, we could still, for a while, look up into the sky and see our planetary buddies further out, continuing to operate as if nothing had happened. For instance, Jupiter would continue orbiting and reflecting light from a sun that no longer existed for about 30 minutes after Earth already knew the sun was gone. And depending on where Jupiter was in its orbit, it would take another 30 minutes to an hour for us to watch the reflected light of Jupiter snuff out. With no moonlight or sunlight, the universe itself would be our only source of visible light from space. In 2004, Abdul Ahad calculated that the Milky Way contributes about as much light as 1/300th of a full moon. So there would be enough light from space for us to see around a bit. But of course, electricity and fossil fuels would still be usable for a while, so cities and towns could continue to be lit by man-made sources, just like a typical night. Except it would be night everywhere. Photosynthesis would stop immediately, and this is huge. I had a great discussion about this video with Henry from Minute Physics and the new channel, Minute Earth. If you're not subscribed to Minute Earth, you definitely should be. In one of his episodes there, he mentions that 99.9% of the natural productivity on Earth is done by photosynthesis, which requires the sun. Without the sun, plants would no longer be able to inhale carbon dioxide and exhale life-sustaining oxygen. But don't worry. Collectively, all of us humans, all 7 billion of us, breathe in about 6 trillion kilos of oxygen every year. But our atmosphere contains a whopping quintillion kilos of oxygen. So even without photosynthesis, and including all of the other animals and insects and microorganisms that consume oxygen, it would take us thousands of years to run out. The poor plants themselves would be much worse off. Without the sun, most of them would die within days or weeks. Except for large plants. Giant trees, for instance, contain enough sugar for energy that they could technically live in the dark for years. Their problem is going to be that the earth will get quite cold. In fact, mighty trees would freeze to death, their blood, the water and sap inside them solidifying, way before they died of starvation. Right now, with our sun, the average surface temperature on Earth, hot places and cold places in different seasons all considered, is an arguably comfortable 14 to 15 degrees Celsius. Without the sun to add energy, the Earth would radiate away heat exponentially, meaning it would go fast at first and then happen more and more slowly. By the end of the first week without the sun, the average surface temperature across Earth would be freezing, 0 Celsius, 32 degrees Fahrenheit. Now, temperatures like this happen all the time on Earth. We're used to it. Panic and fear and looters and anarchy aside, for the first few days or months, we could get by. But by the end of the first year without the sun, the average global surface temperature would be negative 73 degrees Celsius, negative 100 Fahrenheit. The best option, really, would be to move to geothermal areas like Yellowstone or Iceland. These places would be the few safe havens for human life after the sun. Nearly all life on Earth exists because of and is dependent upon extraterrestrial energy, the sun. But the Earth produces its own heat. Despite floating in the coldness of space for billions of years, down below the crust, the Earth is quite warm. 20% of this warmth came from the fact that when the Earth formed, mass crushed so tightly in the middle that the pressure liquefied rock. The other 80% of Earth's internal heat comes from the fact that deep in its core, radioactive elements decay, providing the energy needed to keep the Earth's core at 5,000 degrees Celsius. Anyone who failed to secure a position within one of these bastions of warmth, or perhaps underground in a community warmed and powered by nuclear fuel, would likely be dead within the first year of no sun. In the next 10 or 20 years, things would start to get wet with dew, but not with glorious water droplets, instead droplets of liquid air. The air would literally become cold enough for the gases that make it up to condense or form clouds and precipitate, first as rain and then, as it got colder and colder, eventually as snow. In Fritz Leiber's famous science fiction short story, A Pail of Air, this has already happened. The Earth was ripped away from the sun, and in order to survive, a family must go outdoors in a special suit and scoop up a pail of just the oxygen snow, bring it back in, and place it over a fire to warm and allow them to breathe. A year or so after the sun disappeared, Earth's oceans will have frozen over, ice all the way across. But ice is less dense than liquid water, which means that ice floats. And ice is a pretty decent insulator. So, for billions of years after the sun disappeared, liquid water could still exist at the bottom of our oceans, protected and insulated from space by miles of ice above it, and warmed by vents on the ocean floor that spew water out, superheated by Earth's interior. This would continue on Earth for a very, very long time, sun or no sun. Instead of becoming frozen and lifeless, extremophiles, like microbes that live around hydrothermal vents deep in the ocean, would be fine. They live deep in the ocean, far below the point where sunlight can penetrate, and they make energy not through photosynthesis, but via chemosynthesis, converting heat and methane and sulfur into the energy they need. They are then eaten by clams and tube worms. Extremophiles deposit minerals back into the vents, meaning that their food chain is complete. It's a circle. It's independent of the sun. Earthlings like them would thrive if the sun were to disappear. They would live just fine without ever knowing that the sun was gone, or honestly, without ever even knowing it existed in the first place. It's amazing to think that life here on Earth, all alone, flying through space with no sun, would kind of be fine. Far from becoming a frozen dead rock or a boring dormant seed, the Earth would be a spaceship carrying living passengers with enough geothermal heat for billions of years of life. If the sun disappeared, spaceship Earth would fly out in a straight line, covering about 30 kilometers every single second. After just 1 billion years, it will have covered 900 quadrillion kilometers, or about 100,000 light years. A trip that could potentially take it all the way across our galaxy, near thousands of stars, and nothing's to say it couldn't fall into orbit around one, thaw out, and allow its still living extremophiles to proliferate life on Earth all over again. Maybe one day developing life intelligent enough to uncover whatever is left of our lives. Maybe they could even find this very video. In which case, hi, you're welcome for this video about your planet's history and journey. And as always, thanks for watching.
All right. I know that got a little bit off topic, but I always like showing and watching that video. I think it's a really interesting thought experiment. Any comments on it? All righty then. So what exactly does gravity, how does gravity work according to Albert Einstein? Well, no, I'm not going to do this and then just bounce back and forth. I'm going to pull up another video here. All right. Here we go.
Relativity, the explanation for gravity is that matter bends space. And so you put mass in a place in space, it warps space-time, and objects are not feeling a force of gravity, they're just following the natural curvature. And so this is a sheet of Lycra. Where do you get this? This is my old bike shorts. No, there's literally a spandex.com. You can get a sheet like this if you buy the sale stuff, so you don't care what it looks like, right? For like 20 bucks, maybe less, depending on the sale. And so you put matter and it warps space-time. And so if I have another object, it also warps space-time. They feel that and they're attracted to each other. And so that's Einstein's picture of gravity. Objects warp space-time, feel that curvature, and move accordingly. And if you have more mass,
You're right there on that.
oh, if you have more mass, it's going to bend space-time more. And so if you have objects here, they are going to respond to that, right? And so you put something there, now it's attracted. Now, in reality, that big mass would feel the warping of space-time by the marble too, right? It would move a little bit, but we usually ignore that. You know, the Earth makes the sun move a little bit, but it's so small you can ignore it. The moon makes the Earth kind of wobble around a point 3/4 of the way from the center of the Earth. We usually don't account for that when we're looking at satellite motion. Well, instead of just letting go of one, what if I give it a sideways push? Now it orbits. Now it's losing energy, which wouldn't happen in the solar system, right? Not noticeably. There's some perturbations from other planets and things, but this one does lose energy and spirals in. If I don't push it as hard, it will do an ellipse for a while anyway. And some more here. So one of the things I thought of to do with this is when you study the solar system, all the planets are going around the sun the same way. Why is that? Did God decide that he only liked clockwise, or depends on whether he's above or below the solar system, right? Why is everything going in the same direction? Well, the answer is it wasn't. Different directions. But there was a preferred direction. The disk it formed from had a slight preference one way versus another, and things going the opposite way got eliminated, and when it's all said and done, everything's going the same way. That works 90% of the time.
Is it like the toilet flushing? Southern hemisphere? Wow, can you do that again?
And so, it won't work then. And so I have slightly more in one hand than another, but I don't consciously do that. And you want to get them so they spread out a little when you throw it.
It's because they're colliding with each other that you...
The ones going the wrong way get eliminated, right? Now there also would have been, this is where this analogy breaks down. There's, another dimension, right? But those things that were out of the plane also, that weren't near the preferred plane, also got eliminated. And so that's kind of cool. Now my students use a PHET simulation called My Solar System, and so they've seen all this on the computer, and when we do this during our special relativity unit, they're like, hey, it's just like the computer. That's kind of cool that a stretched sheet of Lycra models things, it's not just like it, but similar to the computer. Now, some things we've discovered using this, also had just some larger marbles, might as well put them out, but they bend space-time too, right? And so maybe, oops, you can get one thing to orbit another. I think I can do a little better. There we go.
Oh my God.
So the Earth-Moon system, maybe? And so you can see that this seam, you can't buy Lycra this big. You get it in rolls, and you have to sew it together. I've been told to use stretchy thread to sew it together. And so next time I do it, I'll do that because it pulls. And so just a little bit of thread fixes it. And so in the morning, when I first set this up, I'll have it leaning against the table. I'll be underneath fixing holes from last year. One time my principal walked in. And I hear somebody in the room, and I'm underneath. I'm in the middle of sewing it. I'm not going to pause yet. And then he's looking around.
All right, so we don't need to watch the rest of that, but I think that visual really helps make sense of how Einstein viewed gravity. And so his theory, or his solution to explaining this idea that gravity is affected by, or excuse me, gravity and its information travels at the speed of light, but also that gravity affects light, comes back to this idea of his called general relativity. So Einstein has two theories: special relativity and general relativity. General relativity is very much about how space and time communicate the force of gravity. So let's see here. And so gravity exerts that influence by being curved, or by curving space-time. So you put a mass in space and it curves the fabric of space-time. And this curvature tells other objects how to move around it. So how do you go about proving something like this? You know, there were a lot of people that were like, no, no, no. Newton's idea of gravity has been, you know, amazingly accurate up to this point in time. Like, there's the why, you know, why fix something that's not broken? And it turned out that there were some issues with Newton's law of universal gravitation. So Einstein was really looking to get his idea proven. And this was his suggestion. Right, so on Earth, we look out and we see a bunch of stars at night. Right? And our eyes like to tell us that light travels in straight lines. You know, so if you see something, you would imagine it's actually located in the direction that you're seeing. An example that you all might be familiar with is when you're driving on a highway and, you know, about a mile down the road, it looks like there's water in the middle of the road, right? It looks like there's a puddle somewhere in the middle of the highway. And then when you actually drive and get to that point, puddle's gone. Well, it wasn't actually a puddle, right? It's light bending, right? So our brains and our eyes are being tricked by this notion that light travels in a straight line, when the reality is it doesn't. Light travels the shortest distance between 2 points. And in space, that shortest distance is often a curved path. That is often a curved path. So, for example, and this is sort of the theory here, and we'll get into how we actually implemented this. During the daytime, there are stars out. We just can't see them because the sun is so bright that it's, you know, like having a whole bunch of glare, right? We can't actually see the other fainter stars in the background. That and our atmosphere is not particularly easy to see through during the daytime. But if we could see stars in the sky during the daytime when the sun is out, Einstein's theory suggests that the perceived position of the star would be different than the actual position of the star. Right, so there might be a star that's behind the sun from the Earth's perspective, whose light passes very close to the sun and is thereby bent to our location on Earth's surface. But when we look out into space, it looks like the star is coming from over here. Right? It looks like this is where the light was located. Right, so how do you go about proving this? Right? How do you make it so that you could see stars during the daytime? Well, it's actually quite ingenious. During a total solar eclipse, there was another scientist whose name was Arthur Eddington, a British scientist. Arthur Eddington and Albert Einstein were in correspondence with each other during World War I, as Einstein was coming up with his ideas for general relativity. And Eddington had had the means of conducting this experiment, right? So Einstein was a theorist. He wasn't like the get in the lab and do things kind of guy. He was writing down the equations, deriving things, and figuring out what should be based on how the math lands. And so during a total solar eclipse, which are predictable, Eddington and one or two other people, part of his scientific team, took an expedition to Africa, and they were in this exact spot where there was supposed to be a solar eclipse coming up, and during the solar eclipse, a total solar eclipse, the moon gets between the Earth and the sun, and it blocks out all of the sunlight, which makes the stars in the background visible. Right? Those stars that are near the sun in the sky would then be visible while the sun is blocked out. And so Arthur Eddington and his team took pictures of those stars on this particular day, and they had the image basically saved on this photo plate. Right? So he has this photo plate with all of the locations of the stars. You can see the total solar eclipse. And they compared this picture, this photo plate, to another photo plate of that same region of the sky at nighttime, at a different time of year when the sun was not out. And when overlaying the two images, the shifting of the apparent position of the stars was pretty much exactly what Einstein predicted it would look like. Right? It was the exact amount of light deflection. And so general relativity is this new theoretical means by which we can explain how gravity works. Right? It is the explanation for how gravity is communicated across space. And most importantly, it solves that conundrum regarding gravity going faster, right? The thing that Newton's equation could not account for, Einstein's equation or his theory does. How many of you remember in 2016, almost five years ago already, there was a big sort of hullabaloo about gravitational waves? How many of you remember hearing about that in the news or reading about it online? Really big talk. Anybody? So if two black holes, two objects that have extremely large gravitational pulls, right? They really warp the fabric of space-time. If two black holes orbit each other, as they spin around each other like this, right? They basically create ripples in the fabric of space-time. And those ripples would travel outward at the speed of light. And 100 years after Einstein predicted gravitational waves, in the year 2016, they were first detected by researchers with a project called LIGO. Let me see if I can actually pull up the sound here. All right, so Einstein's theory of general relativity was pretty much spot on, and it's 100 years later, and we're still like discovering things related to that and proving it right for the first time. It's pretty crazy. Gravitational waves. I think It's like a 10-minute video. We'll watch this, and then we are going to, we're going to be done. Oh, we got 2 more slides, then we'll be done.
Our proven installation process.
You know, so I will actually do those 2 slides after. I'll do the 2 slides first, and then we'll watch the video. All right, so other predictions that come from general relativity are the existence of black holes. So one, it predicts the existence of black holes, but it also helps us understand black holes. It also helps us understand the Big Bang a little bit better, because there's so much mass in such a small amount of space that general relativity applies. General relativity is really useful when you're looking at a lot of mass in a very small place. So like here on Earth, like we don't need to use general relativity to look at the motion of a car going down the street, or you know, a person walking down the sidewalk. We can use Newton's laws of motion, right, for dealing with those things. But it's general relativity, GR, really comes into play when you're looking at things that are very heavy. Okay, we're not going to talk about black holes right now. Well, we're not going to talk about that aspect of black holes right now. We're going to watch a short video, and then we can bid adieu to each other and have a good night. Here we go.
This ensures your gutters are in tip-top shape and prep to protect your home. Step 1, we clean your gutters. Step 2, we realign.
1.3 billion years ago, in a galaxy far, far away, 2 black holes merged. As they violently spiraled into each other, they created traveling distortions in the fabric of space-time, gravitational waves. In the last 1/10 of a second, the energy released in these waves was 50 times greater than the energy being released by everything else in the observable universe combined.
It's like an awe-inspiring kind of energy.
After spreading out through the universe at the speed of light for over 1 billion years, the waves reached Earth, where they stretched and squeezed space such that 2 light beams traveling in perpendicular pipes were put slightly out of step, allowing humans to detect the existence of gravitational waves for the first time. That's a simple enough story to tell, but what I found out when I went to visit Professor Rana Adhikari at Caltech is that it hides the absurdity of just what was required to make that detection.
There's a lot of things about gravitational waves which are absurd.
Hi there, welcome to Forward, come on in. I'm Dr. Nate Favini, I'm our medical lead here.
That's it, yeah.
The main problem with detecting gravitational waves is that they're tiny. They stretch and squeeze space by just 1 part in 10 to the 21. That's the equivalent of measuring the distance between here and Alpha Centauri, and then trying to measure variations in that distance that are the width of a human hair. To detect such tiny wiggles, you have to measure over as large a distance as possible, which is why the arms of the interferometers are 4 kilometers. And even with arms this long, gravitational waves vary the length of the arms by at most 10 to the minus 18 meters. So the detector has to be able to reliably measure distances just 1/10,000th the width of a proton. It's the tiniest measurement ever made. So how is it possible to measure that, considering all the other sources of vibrations and noise in the environment, like earthquakes, traffic, and electrical storms? Well, for one thing, the mirrors are the smoothest ever created. They weigh 40 kilograms or 90 pounds and are suspended by silica threads, just twice the thickness of a hair, to isolate them from their environment. And even then, the only way to be certain not to be tricked by environmental noise was to build 2 detectors far apart from each other in reasonably quiet locations. That allows you to distinguish between local noise, which would appear at only one site, and gravitational waves, which would pass through both sites almost simultaneously. I'm in a building that contains a 1 to 100 scale of LIGO, the gravitational wave detector. The next challenge is the laser.
Whoa. Whoa. It's a lot of stuff.
You need a laser that can provide one and exactly one wavelength.
You can imagine if your laser wavelength is changing and you're trying to use interference of light waves to make this measurement, it's never going to work because it's something like trying to measure this distance, but your ruler stick is constantly changing back and forth. You can't tell how many inches this is. All this equipment, at least 3/4 of it, all we're trying to do is make the laser more stable. And by the end of the day, what we've achieved is something which has a stability of 1 part in 10 to the 20. What does that mean? That's 100 billionth of a trillion. That's kind of what we end up with.
The best lasers for this purpose have a wavelength of 1064 nanometers. That's infrared light. But this presents a problem. How can you measure 10 to the minus 18 with 10 to the minus 6 wavelength of light?
Yes. I wish more people would ask this question.
It's great for this animation to show such a large shift in the wavelength, but the reality is it's only 1 trillionth of a wavelength that the arms are shifting in length. It seems obvious that you can measure half a wavelength because that'll cause the light to interfere with itself.
Yeah, but that's fully. That'll go from completely dark to completely bright.
So are you looking at like slightly darker and slightly brighter?
Yeah. And the limit here to how good we can measure this difference between dark and bright has to do with the fact that the light is discrete. It comes in discrete chunks, which are called photons.
The variation in the number of photons hitting the mirrors at any instant due to this quantum uncertainty is proportional to the square root of the total number of photons. What this means is the more photons you use, the smaller the uncertainty gets as a fraction of the total. This is why the laser power in the arms is 1 megawatt. That is enough energy to power 1,000 homes in a light beam.
And a megawatt, boom. It won't even rip your head off. You just vaporize. It'll be just a smoking stump.
Even with a perfect laser and 1 megawatt of power, anything the light hits would interfere with it, even the air. So all the air in the arms of the detectors had to be eliminated. And it took 40 days to pump down to just 1 trillionth of atmospheric pressure. And the tubes were heated up to the temperature of an oven to expel any residual gases. They pumped out enough air to fill up 2.5 million footballs, making it the second largest vacuum in the world after the Large Hadron Collider. Now here's something most people don't think about, which is that gravitational waves stretch space-time. So light traveling through that space should be stretched as well. If everything is stretching, how do you know anything is stretching?
How do you know anything is stretching? That's the conundrum. It doesn't make any sense. This whole thing is bogus. Shut it down. I would send a laser beam down this tube and then wait for it to come back, and then I would say, well, nothing happened because the space got stretched and the laser wavelength got stretched. It looks the same if it got stretched or not stretched. It doesn't make any sense. Well, it's sort of a matter of timing is how it works. So the amount of time it takes for light to go down this tube and comes back is very short. However, the wave, the gravitational wave, when it comes through, it's doing this slow thing like this noise I made. Which is low. It's a slow stretching. It's only 100 times per second. And it's true, when the wave comes through, the light which is in there, it actually does get stretched. And then that part doesn't do the measurement for us. But now that the space has stretched, that laser light is like come and gone. It's out of the picture. We're constantly shooting the laser back into the system. So the new fresh light now goes through there and has to travel a bigger distance than the light before. And so by looking at how this interference changes with time and keeping the laser wavelength from the laser itself fixed, we're able to do the measurement.
So what was needed to detect gravitational waves? Well, a megawatt of laser power to minimize shot noise of exactly 1 wavelength, because we're trying to measure just 1 trillionth of that wavelength. Continually inserted to replace older light that's been stretched and squished in the world's second largest vacuum chamber at just 1 trillionth of atmospheric pressure, hitting the smoothest mirrors ever created, suspended by silica threads, at 2 distant sites to eliminate noise, with 4-kilometer long arms to increase the magnitude of gravitational waves to just 1,000th of the width of a proton.
What we already do daily in here is what I would have said is impossible if you'd asked me about it 20 years ago.
One of the things that was most interesting for me to learn was what is limiting the sensitivity of the detectors today. And it turns out it is quantum mechanics, and essentially you can think of it like a Heisenberg uncertainty principle. We've got two things, and together their uncertainty has to be bigger than a certain value.
Luckily, for us, we're only trying to measure one thing here. We're not trying to measure two things at the same time. All we want to know is how much more did this arm get stretched from that arm? And that's the key point, which people did not understand until recently. The way to build these systems is such that they're extremely good in measuring one thing, and that all of the uncertainty which comes from quantum mechanics is completely crammed into this other thing that we don't care about.
I feel like we're getting down to these levels of nature where it seems like nature doesn't want you to go any further. But through our ingenuity, we're figuring out ways to engineer quantum noise. I think that's such a remarkable concept, and I look forward to the results that it's going to bring.
I think the next logical step is to go from two signals to detecting all the black holes in the universe all of the time. It's not like an alien civilization level of technology. It's just, we have to do a lot better than what we're doing now, but I see it sort of within.
All right, that was a really weird time for an ad to start with like 6 seconds left of the video. I just want to hear, or I want you to hear the sound of gravitational waves. Hold on a second, where is it? All right, so these were the sounds that were detected. Here we go. So they basically took this detection, right? The frequencies that were recorded due to the gravitational wave, and they converted it into a sound wave electronically. Sorry, they're playing the sound on repeat. It's like with the water droplet at the end. That is the sound of the gravitational waves. And the video is showing the merging of those two black holes. And that is the conclusion of our lesson tonight. Talking a little bit about how gravity affects light, how gravitational information travels at the speed of light, how Einstein's theory of general relativity explains this idea of the space-time fabric and major warpings of due to gravity, gravitational waves. And so we've touched on a couple of really important ideas, and I encourage you to do a little bit of research on your own if you're interested. And with that, have a great night. We are done. So I'll stick around if anybody has any specific questions. Otherwise, I'm stopping the recording, and take care.